Welcome to lecture 1.4, co-simulation. Today we will see what co-simulation is and how it works. Let's assume we have a real power system. In this case, a distribution system with electric vehicle charging poles. These poles can communicate, and by that they can check market prices, and maybe even do forecasts of day-ahead prices. This would allow them to charge a car in a smart way. Additionally, there is the car itself. Sometimes it disappears, sometimes it's plugged in, and the car has a battery. There is power electronics involved as well. And now you would like to optimize this. Maybe the goal of your optimization is better market rules. They should be efficient, or have a guaranteed convergence, or they should be very fair or very fast. Other goals of your analysis could be control algorithms that help solve voltage problems on the distribution grid. Or you would like to optimize, or actually maximize, the lifetime of the battery. Often we have such multiple goals and requirements, and we want them all to be satisfied somehow. If you optimize for only one of these goals, you might ignore or forget the others. The way out of this is models that cover all involved mechanisms. Models that can be executed with a numerical solver. Individual subproblems, represented in submodels, can be executed in sub-simulators. You just have to hook them up somehow, so that they can interact. They have multiple mutual dependencies in the end. The power electronic charging simulation interacts with the communication network simulator, and by that can send a message to a market simulator where decisions are done or bids are matched. So the real system is translated into a simulated one where every physical subdomain or every domain of computation has its own simulator assigned. Typically, this is done with a co-simulation framework. Co-simulation means concurrent or coupled simulations, where multiple simulators interact. This sounds simple, but it's not. Every simulator has its own little submodel described with differential equations or some other modeling philosophy, and also a numerical solver. Each simulator has a model and a solver, and these simulators share simulation variables. The energy storage simulator, for instance, shares the voltage of the charging station with the grid simulator. Unfortunately, each simulator has its own version of reality of such variables. One says it's 500 volts, the other one believes it's 490, and a potential third one might believe it's 510 volts. In reality, however, there's only one ground truth, one voltage. So these simulators have to iterate until they agree on one shared reality. Such iterations happen at every time step. Once the co-simulation steps in time, maybe in milliseconds or in seconds, into the future, all the simulators must iterate and agree on all shared variables at each step. And that is pretty tedious. And this is what this co-simulation framework does. It helps. It helps synchronizing variables. It helps in stepping in time. And sophisticated ones can even step back in time if they forgot something. The co-simulation framework is in the middle of all these simulators and coordinates the overall system simulation. There are many things to consider. Let's go through a few of them. First, you have to know what you're modeling. Typically, you have some physics, such as the electricity network. A simple model for power grids would be static, based on power flow equations. They are easy to calculate. If you have dynamic models, it gets a bit more difficult, but there are even other models that you might want to consider. If you have, for instance, a transformer, and you would like to know how it heats up or how fast it ages, then you might need a thermal model or even a 3D model with finite elements or even computational fluid dynamics. The power grid model and the transformer models might be in different simulators because we need specialized solvers and libraries. Another category of models that you might need are discrete models, such as network communication simulators, where you see all the ICT impact. They can cover communication latencies and packet loss in your communication network. They can also feature specialized protocols, such as IEC 61850. This diversity of models and solvers requires a co-simulation framework. It can connect physical models among themselves and with discrete ones. There are a couple of such frameworks out there, open source ones like Helix and Mosaic, and specifications like the functional mockup interface that provides a simple C interface for simulators. Beside the physical and the digital parts of your smart grid, there are many other things that you might want to consider. The energy markets, maybe the environment, or some regulatory mechanisms, for instance, all that can interact with your energy system. On top of that, let's not forget computational efficiency. I already mentioned the synchronization of the shared variables. This and other mechanisms in the co-simulation are very, very costly. If you don't design it properly, co-simulation is slow. So you might want to optimize it, maybe even for certain hardware. Sometimes you have parallel hardware or powerful cloud platforms where it can run a bit better. But the models must also match that hardware. Sometimes you have hardware in the loop, HIL, H-I-L, a real device that you want to interact with the simulation. In case of power hardware, this even involves a power amplifier. Only real-time simulation is capable of doing hardware in the loop because reality is in real time. Sometimes you can simplify models in a smart way. Machine learning gives the option of generating surrogate models trained for a certain purpose. And they can do one particular job very fast. While they will not be able to tell you everything, they will at least tell you what you would like to know in a very efficient way. Here's an example of such a setup where the charging of a smart car was simulated, and we played around with the communication network that was connecting the charging poles with the energy markets. The impact of latencies and packet loss on the control performance was the subject of interest. The starting point is a voltage violation. It dips down below a threshold, and then the controllers should react. And they do react. They talk to each other, and all charging stations in one street try to fix the situation together. And this simulation shows all the details, which is maybe the big blessing of co-simulation. You don't have to sacrifice details. The battery model is detailed. The power electronic model is detailed. The communication system model is detailed, and so on. You don't have to simplify just because you have only one simulator which is good in simulating batteries. Having one such simulator means all the other parts of the system have to be simplified and squeezed into the modeling abilities of this unsuited simulator. With co-simulation, you can use dedicated simulation platforms and environments that work with validated libraries that are specialized for this particular aspect of the system. This simulation setup shows the impact of communication latencies, more voltage violation with more latencies. And at the same time, it covers battery aging and loading of power electronics. Why? Because each of these parts have dedicated, detailed models. This means co-simulation is capable of having a multi-focus. You can optimize the communication network while not forgetting the health of the battery, the voltage on the distribution grid, and market fairness. This is all covered by the simulators, maybe even done by a team of experts working with them. This all sounds fantastic, but in reality, it's of course not so easy. Sometimes you don't have the right data to create your models. There is a lot of uncertainty and many things you don't know, so we have to make assumptions, and the computational complexity is very high. The iterative synchronization that I mentioned is a trade-off. You can synchronize more to be more accurate, but that also takes more time. There are even elements of systems that you cannot model at all. Some controllers are black box. You don't know what is inside. In this case, you have to do hardware in the loop. You connect the real controllers to the simulation and see how they perform, how they behave. The power system interacts with other systems, with markets, with the transport system, with the built environment, and with the society at large. And that doesn't make things easier. How do you cover such complex parts? And ever more, co-simulation cannot be the answer, since in the end, you also want to validate it. It's easy to validate a component, a machine. If you have a real machine and you have a model, you can make experiments until your model forecasts the behavior accurately. But with a system that has the size of a continent, you cannot replicate that in your backyard, and you cannot make experiments with it. So it's rather hard to do validation with this. All right, today we have seen co-simulation, a fantastic tool. It helps you to investigate complex systems. You can decompose the system in smaller parts where you have a model and a solver that can cover that very, very accurately. These individual submodels can be connected with a co-simulation framework that takes care of all the synchronization and time stepping that is needed. With that, you can simulate heterogeneous power system that consists of different types of physics, communication networks, markets, and so forth.